Hi everyone, I'm Qinghua, a PhD student at Princeton University. In this video, I will talk about our recent paper, Sample Efficient Reinforcement Learning of Undercomplete POMDPs. This is a joint work with my advisor Zhi, also from Princeton, Sham Kakade from University of Washington and Microsoft, and Akshay Krishnamurthy from Microsoft New York. Let's start. In many real-world reinforcement learning applications, there is a very challenging feature called partial observability. It means that an agent cannot directly observe its current state in the environment and only have access to partial or inexact information. For example, in poker games, a player can only see his own cards and possibly the common cards on the desk. He doesn't know what his opponents have in hands. Another example is robotics. Usually, a robot can only see things in front of its camera. POMDP is a classical and popular model that can abstract and describe such partial observability feature. Different from MDPs, in POMDPs, you can't directly access your current state. You can only observe an observation, which is sampled from a distribution determined by the current state. In other words, you may think of a POMDP as a combination of an MDP and a hidden Markov model. Compared with learning MDPs, the main challenge of learning POMDPs is that the stochastic process is not Markovian on the current observation and action. So, in order to make the best decision, or to infer the distribution of the underlying state, the agent may need to look at the whole trajectory of actions and observations, which can have exponential possibilities. Alternatively, if you want to trivially represent a POMDP by an MDP, the cardinality of your state set will increase by an exponential factor. Due to the partial observability feature, there have been many hardness results about learning POMDPs. For planning, it has been shown by Papidemetriou, Thysicles, and Velasquez that computing the optimal policy for a given POMDP model is NP hard in general. And for parameter estimation, Mason and Rock proved that estimating the parameters of a hidden Markov model is at least as hard as learning parity with noise. Since HMM is a special case of POMDP without control, this result directly implies that estimating POMDPs is also hard. Luckily, all these barriers are in computational sense. They don't exclude the possibility of statistically efficient learning of POMDPs. And actually, in the following slides, I will show you that for a rich class of POMDPs, our algorithm can find a nearly optimal policy within polynomial samples. Before introducing our work, I want to quickly go through some existing related results. Guo et al. Applied tensor method to learn POMDP under the assumption that the initial distribution is uniformly supported on the state side. This allows for estimating the entire model without exploration. Here, by exploration, we mean the algorithm should try to figure out how to reach unknown states efficiently, which is particularly challenging in POMDP because we can't see if we have reached some new states like in MDPs. And in Azizi and Shali et al., they only consider policies that can visit every state. As with the first work, this restriction guarantees that the entire model can be estimated regardless of the policy executed. So again, sophisticated exploration is not required. In summary, previous results didn't mitigate the exploration challenge in reinforcement learning, and one of the main contributions of our work is that we proposed the first sample-efficient algorithm that directly deal with the exploration challenge without making similar assumptions. Now, let me introduce you the basic settings and main results of our work. Formally, in a POMDP, we have a state set, an action set, and an observation set. We have a transition measure, which specifies the probability of transiting to state S prime from state S by taking action A. We also have an observation measure specifying the probability of observing O at state S. In this work, we consider the finite horizon setting with length h, and the reward is a function of the observation sequence. With make two standard assumptions. The number of observations is no smaller than the number of states, and the minimum singular value of the observation matrices is lower bounded. The reason for making assumption B is that if several states have linearly dependent observation measures, we will be unable to distinguish them and may encounter some hardness. Under assumption 1, we proved that an epsilon optimal policy can be found using polynomial samples in all relevant quantities. Here, capital S is the number of states, capital A is the number of actions, and capital O is the number of observations. Capital H is the length of horizon. Alpha is the lower bound for the singular value of the observation matrices. Here, the dependence on epsilon is optimal, because even in Bandit's problem, 1 over epsilon squared is already optimal. Moreover, to necessitate our assumptions, we proved that with absence of either assumption A or assumption B, learning a POMDP needs at least exponential samples in general. To the best of our knowledge, this is the first sample efficiency result for learning a class of POMDPs, where exploration is essential. The algorithm achieving the upper bound is built upon the observable operator models. In observable operator models, the probability of every observation sequence can be written as products of operators. One can verify that POMDPs is a subclass of OOMs in the sense that for every POMDP, there exists a set of operators that can be used to compute the probability of every observation sequence. Therefore, in order to predict the dynamics of a POMDP, it suffices to only learn its operators. One advantage of using this operator view is that these operators are indexed by observations and actions, not by the invisible underlying states. So the question is how to estimate these operators. One naive way is to simply try every action sequence and estimate the corresponding distribution of observation sequences. This method will blow up the sample complexity exponentially. Instead, in our algorithm, we utilize a moments constraint for operators. To give you a taste of what this constraint looks like, we take the second step as an example. The same holds true for other steps. Here, P21 is the joint distribution of the first two observations conditioning on the first two actions being fixed to be A tilde and A. Similarly, P301 is a slice of the joint distribution of the first three observations. When constructing the confidence set, we replace the relevant probability matrices by their empirical estimates. And the confidence level of our estimate can be determined using standard multiple concentrations. Now, I'd like to introduce you our algorithm OOM-UCB, which represents observable operator models with upper confidence bound. In each iteration of OOM-UCB, first, we compute an optimistic policy using the confidence set. Then we collect data by running the optimistic policy. And finally, we update the confidence set using the newly collected data. The sample complexity is polynomial in all relevant quantities, and in particular, optimal in epsilon. Our algorithm looks very simple, but in our analysis, we developed many new techniques to relate the moments constraint to prediction error, which is highly non-trivial, because in the moment constraint, it only looks at every 3 consecutive observations. While it can guarantee prediction accuracy for an observation sequence of length more than 3. Due to time limit, I will not answer this question. If you are interested in the answer, please refer to our archive paper. In summary, we proposed the first sample-efficient algorithm for reinforcement learning of POMDPs, where exploration is essential. Thank you for watching.